So we jumped ahead to looking at these high and low pressures in the Hadley, Ferrel, and polar cells, north and south latitudes on scales between January and July. And January and July meaning that the Earth's 90 degrees sunlight angle, so the sun is hitting most directly during the January months at 23.5 degrees south, and in the July months, they're hitting more directly up near 23.5 degrees north. And so that means this natural 6-month shift is showing the shift of high and low pressures on their two most extremes. And they migrate back and forth dependent on time of year. Now I'm going to flip from this page to a blow up of these two images so that we can look at them more closely. So this is the January month, and we can see this is my intertropical convergence zone. And so I have my natural low pressure on this belt along here. And notice that the low pressure will sink more southerly or more northernly inland. So those high and low pressures will persist inland a little farther north or a little farther south, dependent on time of year as well as landmass. The fact that land is in the way changes the natural highs and lows and where they would occur. And so I have my intertropical convergence zone, and then my Hadley cell will have its natural rising in the aloft of the atmosphere, diverge aloft, and then it's sinking along these high pressure zones. And we can see here it's around 30, but then inland it sinks up towards 50 and then goes back down towards 30 and then way up near 50 again on the north. And down below where I have my natural oceanic currents and not a lot of landmass, I can expect it to sink a little bit towards 35, but to be right around 35 to 40 based on the January time of year, because there's not a lot of landmass in the way here. And then where I don't see any landmass in the way, I can expect my norm. Now, this slide is the blow up of July. And so July, it's shifting northward, my high and low pressures, and you can see my intertropical convergence zone has shifted north. And where there's landmass, it pushes inland, right? I can also see the variation in monsoon season where the wind shift would occur, because all of a sudden I bring the rain, right? Monsoon season. So I'm bringing the wind shift, which brings in the rain, and the low pressure kind of sinks inland. And you can see the low pressure sinks inland and kind of takes over a lot of the Eurasian regions and brings in the wet weather. Same thing with the sub-Saharan African regions. This brings the rainy season, right, as it shifts in. Here's the Bermuda High, which creates the pressure system, which doesn't allow air to flow through, hence Bermuda Triangle, people getting stuck, not being able to cruise through the region because it's a natural high pressure. So I have air just naturally sinking and no cross breathing. So I have no breezing moving on the horizontal. All my breezing is moving vertically down through the troposphere, sinking into that region. Not a lot of air action, not a lot of cloud growth. Low pressure system shifting inland over here, bringing in some wet seas into my desert regions, and then we see my high pressures have shifted north in this location. Low pressures have also shifted north, and in some locations like Iceland is a beautiful green place during this time of year, and some of that has to do with the natural rain currents that are occurring in this location. And then once again, where I see very little land mass, I have sort of my natural, so right around 30, here's my high pressure system, right? As we go through, and you think of the middle of Australia being desert, right? So it fits all these things that we're talking about with the Ferrel cell. And then this again is my polar cell up above, and my high pressures would be very high north in this case. So these are the natural shifts. So going back, the shift up and down of my high and low pressures on the north and south, depending on time of year, creates natural wind currents and changes in those wind currents. All right, so this brings us into looking at the air in different measurements. And one of the things that you'll notice on maps is what they call millibars of pressure. And these are isobar line maps. And so they're looking at isobars or pressure lines, and they're showing you at variation of altitude different isobars. And that's because if I was doing something like flying, I might want to stay within a jet stream, and that's coming up in a few slides. I might want to stay within a jet stream, or I might want to stay out of the jet stream so that I'm not working against the wind. And in order to do that, I might have to change altitude to flow with that pressure regime. And so here we have a area that is 30 degrees north latitude, and this is 80 degrees north latitude. So you almost have to think of this image as being turned on its angle, and this being near the North Pole, right? And this being towards the equator, if I'm turning it up, right? And I'm looking at different altitudes. And so I can see my 1,000 millibars on the surface, my 1,000 millibars on the surface down here, but then the altitude, which with my 900 millibars around 30 is much taller than it is over here at 80. Same thing as my millibars of pressure, where I would read, if I was taking isobar lines and I was reading off my pressure regions, I would see that my pressure and my altitude with which I would find the 800 millibars will be higher at the 30 and lower at the 80, and same thing at the 700 millibar line. And this goes into way back in the earlier modules where I said that the place where the troposphere ends and the the tropopause picks up, and then the stratosphere picks up, all these can actually change altitude. This goes into these isobar lines of pressure, and where I can expect the regimes to change, and the actual height of my atmosphere is kind of wavy and bumpy. And like I said, it's a little fatter at the equatorial zones, and it's a little skinnier at the top. So it's wide at the belt, right? In the center. This brings me into thinking of different fronts or air masses in movement. And we can think of places as being a polar front and jet streams. The polar front is a strong boundary that happens to be between the polar cell and the Ferrel cell, and it's a place where Rossby waves, which are coming up in a few slides too, tend to form along this line, which also brings in a lot of storm events, specifically mid-latitude cyclones, which is something that'll come up in a few modules. Not in this module, but the next module set. We'll start talking about mid-latitude cyclones along Rossby waves, specifically on the polar front, which is that low pressure belt around 60, where the air is naturally rising and creating this wet weather, but it's a cold wet weather. There's some jet streams, and there's actually two. They both take place in the westerly winds. They both take place in the Ferrel cell. And the first one is the one that we often think of as the jet stream itself. So when you hear the generic term jet stream, the one that we're thinking of is the polar jet stream. It's the faster of the two, and it's the more consistent of the two. It tends to be flowing at about 250 miles per hour and about all year round. It just shifts a little north and shifts a little south dependent on time of year. The other one is the subtropic jet stream. Now, the subtropic jet stream takes place in the westerly winds, again, in the Ferrel cell, and there's one in the northern hemisphere, and there's one in the southern hemisphere Ferrel cells. So there's polar jet streams in both the south and the north, and there are subtropic jet streams in both the south and the north. And the subtropic jet stream takes place just north of about 30 degrees north latitude and just south of 30 degrees south latitude. And it tends to only run at certain times of year. It tends to be a little bit slower, and it can get interrupted and kind of end. So it drops off at times and then picks back up with its speedy delivery of moving really fast. Jet streams themselves are working on the fact that air is a fluid, and therefore it can flow like a river from high and low pressure zones at high speed. And so that's what it's doing. It's moving at high speed. And so right here we can see an example of my polar jet stream. And right here is my subtropic jet stream. And like I said, when we refer to the term jet stream, I promise you we're referring to this polar jet stream pretty much all the time. But here's my subtropic jet stream. And I said sometimes it ends midway through. Now I'm going to flip over to a video that I think does a nice job in encapsulating all this, so I'm not talking too much, and then we will pick up with a part 3 on all of this.